Welcome folks to this new tutorial on how to use LTSPICE, and this tutorial will be specialized on op amps. So we're going to show you how to use op amps in LTSPICE, and this tutorial is intermediate level, so we will start from the beginning but we will ramp up fairly quickly. Let's get started. The first thing I'm going to do is I'm going to load LTSPICE, so let's get started. So I'm going to come to the LTSPICE icon over here. I'm going to double click on it. I start LTSPICE. So the first thing I'm going to do in this tutorial is to show you how to draw op amp circuits nice and neat, and then we will call the OP27 op amp. It's a special op amp that we commonly used in our laboratory, the electrical engineering laboratory here at Washington State University. So I will start a new schematic. The first thing I'm gonna do when I use op amp is to define the power supplies, so which are the real voltages. So I'm gonna start with adding components here. I'm gonna add 2 voltages. So this is V1. I'll do the same thing for V2. So one will be called VCC, the other one will be called VEE. So I can change the name here. I'll call this VCC, and I'll call this VEE, and then I will ground this and that. I will give this a value of 15 volts, and the value of this one going to be negative 15 volts. So the real voltages to run the op amp is going to be plus 15 volts and negative 15 volts. Then I'm going to use label net, and label net basically will say that a net means a node. So the node going to have a label or a name. So I will use the first one. I will call it VCC. I will add that to this one. And the second one, I will call it VEE, and I will add it to the second one. So what basically means is that this node now has the name VCC, and this node has the name VEE, and I can connect this node anywhere in the circuit using label nets, and that will make the drawing looks much nicer and neat. Let me zoom out a little bit. Let's move the panel a little bit over here. Then I'm gonna go to component, and I'm gonna call the OP27. So it is an op amp that we use. So at this point, I'm gonna save this file. What I end up doing here is that I have called this op amp, and I have called this op amp from a library. This library will model this op amp. It has a model for this op amp that describes the behavior, the way this op amp works, the behavior of the op amp. So let's show you how this is done. So I'm gonna go to View. I will look at SPICE netlist. Now remember that SPICE netlist is basically a file that describes the circuit. So let's see what's going on here, right? So we are interested in this command here. X means it's a sub-circuit. We have a sub-circuit. U1 means like the component one, the chip one. And then it gave us the nodes, defines the pins to this sub-circuit, right? So this is a sub-circuit, defines its nodes, its pins. Starts with node NC001, which is this one, NC02, which is this one. Then it goes to the power supply, which is this, that's NC3. NC4 is here, that's not connected, node 4. Finally, NC5, which is here. What it says then is that it's going to use the model. This sub-circuit has a name. This name is called OP27. So this OP27 as a sub-circuit is located in this library, which is called the ADI, Analog Devices Library. ADI. So the Analog Devices Library will contain a subcircuit called OP27. So let's locate this library and let's look the OP27. Where is it located? So I'm gonna go to over here. So I'm gonna go to the C directory. That's where is my main directory is in my computer. And I'm gonna look for programs file. This is Windows based, by the way. I will look for the folder LTC. That's LTSPICE 17. That's the version we have. I'll go under libraries. I will go under sub. And I will look for the ADI library because that's the library we are using over here. So this is just insights to what's going on. So it's not just the schematics that you draw that are important and meaningful, but also, you know, how we are calling those components. So I'm going to go to the ADI. This is a library. I opened it with the notepad. Make sure not to save it or port it somewhere else. So this is the notepad where it has all components. It's a long file, right? So I'm going to go to the top, and then I'm going to do Control F. That means search. I will search for the OP27. I'll do exact match, and it will look for the OP27 in my file. So I will do find next. It did find it over here. So I'm going to do close here. And you can see that starts with this here. It says subcircuit. Subcircuit is a command. You have the dot. Subcircuit. It called it OP27. And it defines the pins. 1, 2, 3, 4, 5. Right? Those are the pins I just showed you. But more important is the equivalent circuit of the op-amp is described here. So this is the model used to describe the op-amp. So let's close this here, close that here. I closed it. Okay, no, did I? No, it's still here. Okay, so it's still here. Okay, good. Okay, so this op-amp here, its behavior is described by this model. And that's what I want you to see. Because when you use electronic simulations with any software, any SPICE software, any components you're going to add, it's going to have a model. So the op-amps are modeled using sub-circuits. And the model contains transistors and diodes and resistors and gains. It's not the exact circuit that builds the OP. It's a model that describes this OP, this op-amp, right? And keep in mind that this discussion is a little bit advanced, which means a little bit beyond circuits, right? You need to know that this op-amp is modeled using sub-circuits. It's important to know that. Anyway, so now we know that this is the op-amp. Now what I'm going to do is I'm going to add the rail voltages. So I will go to label net. I'll do VCC. Okay. I will add the VCC to the plus here. And then I will go to label net. I will do VEE. And I will add the VEE to the negative rail. So you can see that this is much nicer drawing than having a wire going all the way to here and the wire coming all the way to there. It doesn't look as neat. Using the label net makes it much nicer. A couple of things that we are interested in. The first one is we're going to do non-inverting amplifier. We're going to do the non-inverting amplifier with a gain of 20. Then I'm going to show you that at low frequency it will behave very close to the ideal case. But then as we increase the frequency, the gain gonna drop, and then we gonna build on that. Right? Let's basically add the resistor here. So I'm gonna rotate, then flip, mirror. This is gonna be my R1, and this is gonna be my R2, which is the feedback resistor. And then I'm gonna connect this to that. This here all the way to the feedback, and then I will make this resistor to equal to 19K and this resistor here to be 1K. So a couple of things, when you pick up those values you have to be careful, because you know that there is a maximum current that flow out of the op-amp, there is maximum current IO max. You shouldn't exceed IO max. If you do, then the op-amp departs the linear region. It's not going to work as nice. So to do that, then the resistors got to be bigger than, at minimum, 500 ohms. So any of the resistors here got to be bigger than 500 ohms. In reality, that depends on what your Vout is. If your Vout is going all the way to 15 volts, you might even use 1k ohm resistor as a minimum value. Another thing is that you can't use very, very large resistors. You can't say that this is going to be 100 meg. The reason is there is a small leakage current going into the op-amp. It's not zero, right? So there is current going to the op-amp, and that is small. We call it the input bias current or the input offset current. And this is very small current, so you can't use very large resistors, because if the resistor here is very large, the current going through it is very small. This small current, when it comes over here, it's going to branch. So now you depart from the ideal case. So I would say that don't use any resistor higher than 100K, so that you don't worry about this leakage current. Now there is some special op-amps with very small bias input currents. So, but in general, there will be some input bias current going into the op-amp. It's not zero, and that's why you wanted to make sure that the value of the resistors, the biggest values of the resistors, are moderate. Right? I'm going to ground the other side of R1 here. So we are doing the non-inverting amplifier. The gain is 1 plus R2 over R1. So here we can have a gain of 20. I'm going to add an input voltage. So I will add a voltage. And I'm going to keep it a sine wave here at 1000 hertz. And I'm going to call this voltage to be Vn. So let's say that the voltage is going to be a sine wave. And let's say that the input gonna be 10 millivolt at 1000 hertz at 1K. Let me zoom out a little bit. Yeah, it can be done here. Okay. Yeah, good. Okay. So I'm gonna add the ground here. So this is the op-amp completed. Now we need to define the simulation. So I'm going to simulate it for 20 cycles. So I'm going to go to simulate, edit simulation, 20 cycles. Each cycle is 1 millisecond, right? Because the frequency is 1K, the time period is 1 millisecond. So 20 cycles will be 20 milli. And usually the maximum step size, a good number, gonna be 1 over 1000 of the time period. So this is gonna be 1 micro. That's a good number to use. I'm gonna put it somewhere over here. So you wanna make sure that things are nice and neat. And you know, so that's something to keep in mind. Now what I'm interested in is I'm gonna simulate the circuit. So let's run the simulation. I'm gonna draw Vout. So you can see that we have a gain of 20. It's very nice and beautiful sine wave. Now the question is, would I get the same gain at very high frequency? So let's find out, and let's see what's gonna happen if we increase the frequency. So I'm gonna close this. I'm gonna make this max. Now I'm gonna come to the VI. I'm gonna make the frequency to be, I'm gonna do 1 meg. So 1 megahertz. So it's 1 megahertz, and here I'm going to have 1 meg is 1 micro, so we're gonna say 20 micro, and then here it's gonna be 1 nano, right? So I made the transient simulation to run 20 cycles again, and then maximum step size is gonna be 1 over 1000 of the time period. Let's simulate the circuit and see what we get at this frequency. So a couple of things you need to see is that early on the circuit haven't settled yet, right? There is, we call it the transient effect. So that's something you need to watch for, the transient effect. But over here it's settled, it reached the final value. And we can see that the gain over here, right, is not a gain of 20, right? It's much lower, right? And I can use the cursor, and I can do the peak-to-peak cursor. So I'm gonna do this here is at min. So let's do the second cursor here. Again, like I said before in previous videos, that we use in our eyeball here. So we're gonna be very close. So you can see that the difference, cursor 2 minus cursor 1, this is the peak is around 150 millivolt, and it should be 400 millivolts, right? Peak to peak. It's roughly about a gain of 7.7, right? More or less. So it's not a gain of 20. The gain dropped. A better way to see that is to use the AC sweep. So I'm gonna come here to the voltage source, right click on it. I don't need to apply a sine wave anymore. I wanted to apply an AC sweep, so I will do an AC sweep of 0.1 volt. AC sweep. Let's go back here. None, right? AC sweep 0.1. Okay, that's what it is. And then over here, I'm gonna edit my simulation. You just come to the command, right click on it, and I don't need to do transient. I'm gonna do AC sweep. So, and then on the AC sweep, I'll do a decade. It will be 1,000 points. And then I will start from, let's say, like 10 hertz to 10 meg. And let's see what kind of behavior would we get, right? So now we use an AC sweep here. Let's zoom in to show you that. So we use an AC analysis, right? It's a decade. The samples per decade is 1,000 points. I will start from 10 hertz to 10 megahertz, and the input signal is 0.1. So I'm gonna simulate. I wanted to know what's the input voltage. The input voltage is at node N003, and it reads negative 20 dB all the way through, which is a voltage of 0.1, right? It's all the way through for all frequencies. Here is our Vout. So, and then what I want to do is I wanted to find the gain, which is Vout over Vi. So I'm going to come on the top of this label here, and I'm going to right click on it, not left click. Left click will give you the cursor. You don't need the cursor, you need to edit it. So I'm going to do that. This is the output. I'm going to divide by the input, which is divide by V. I will open parenthesis, and then it is N003, close parenthesis. I would like to change the color to make it much better. I will use the red color. And that's our gain. So you can see that the gain here is roughly 26 dB. That's a gain of 20. And then at higher frequencies start to drop, right? So the gain of the circuit is not going to be a gain of 20 for all frequencies. If you apply 1 megahertz, we dropped dramatically, right? At 10 megahertz, definitely going to drop even more. So let's determine the cutoff frequency of this gain. I don't need the green line, so I'm going to basically delete that. So I see that this is the gain. Now I'm going to use the cursor to show me the gain. So I'm going to click on the cursor twice. The first one will read the DC value at low frequency here. You can see that the gain is 26 dB, right? It's a gain of 20, right? A gain of 20 will give you 26 dB. I'll click on the cursor again, right? Acts as a low pass filter, so I'm going to look at 3 dB below that. So I'm looking at the gain. If I move this over here, the gain going to be around 23 dB, right? So I'm going to move the cursor until I get 23 dB. And more or less, I don't have to be accurate here. It's around 491 kilohertz, right? So at 491 kilohertz, the gain here is 3 dB below the DC gain. The DC gain is the ideal gain, a gain of 21, right? However, at 491 kilohertz, the gain here is 3 dB below. That means that the gain here is 70.7% times the DC gain. At 1 meg, the way we did it at 1 meg. So if I move to the 1 meg here, right, the gain was 17 dB. It was roughly 9 dB below the ideal gain. We dropped dramatically, right? So what's important here is that the gain going to be a function of frequency. And the question is why, right? So why the gain is a function of frequency? And the answer is that the op-amp itself is a function of frequency. The reason is there is capacitors inside the op-amp that are added to make the op-amp stable under unity gain feedback. So it's internally compensated op-amp to make it a function of frequency. So what I'm going to do next, I'm going to show you what's the op-amp gain is, and you're going to see that the op-amp gain going to be a function of frequency. So if the op-amp is a function of frequency and it is the engine that drives like a car drives the overall circuit, it's the engine that drives the overall circuit, then the overall circuit can't exceed the op-amp. It will be limited by the performance of the op-amp. So what I'm going to do is I'm going to show you, this is our output, right? And this node here is the input, and this node here is the other input, right? So I will basically say that I'm going to plot the output over the input difference. I'm going to come to the green line here, and I will say that this is the output. I'm going to divide it by the differential input. The differential input going to be V N003 minus V N001. Basically what I said here is that the output voltage, which is VN002, divided by the differential input. The differential input gonna be VN003 minus VN001. I'm gonna click on that, and the green is the op-amp gain. I'm gonna delete now the red and the blue. I don't need those. So this is the op-amp. This is the gain of the op-amp. What I'm doing here is I'm looking into this op-amp. So let's zoom in a little bit here. I'm looking at the op-amp here, and I'm saying that let's look at the differential input and look at the output, and then get the gain from the output to the differential input. And we can see that the op-amp itself is a function of frequency, like the way it's supposed to be, right? Now what I'm going to do is I'm going to say that let's plot the gain of the output over the input. So here is my output. I will make this in red color, and it's going to be the output divided by the input, which is V N003. So the red color over here, this is the gain of the overall circuit, right? So if I'm over here, let's select that. So the gain of V out over VI, right, is the red color here. You can see it's 26 dB, constant, until it came over here. When it came in over here, this is the op-amp, that is the driving engine, and this is here is the overall circuit. You can see that overall circuit doesn't exceed the op-amp, right? The op-amp is the one that will force the overall amplifier to follow it, right? That's important to know. It's important to know that. It's very important to know that. So, when you use op amps to amplify circuits, the first thing you want to look at is, what's the cutoff frequency of the amplifier, right? Which is something that is extremely important to know. All right, so there is a couple of things we also need to know. This is not sufficient. So this here is not sufficient. You need to also test the slew rate. The slew rate is basically the maximum dV out dt. So what's the maximum rate of change of the output with respect to time? That's called the slew rate. So let's close this here. The frequency response by itself is not sufficient. We know that if you increase the frequency, the gain will drop. But there is something more important also associated with that. Is called the slew rate. The slew rate is defined as the maximum dV out dt. Now for the sine wave, we know that the derivative, right, the maximum derivative with respect to time is the slew rate. The derivative is also proportional to the frequency. So if you apply a sine wave at high frequency, there is a possibility that it will be distorted. And let's show you how we can do that. So I'm gonna come to this AC analysis. We're gonna delete that. I don't need AC analysis. And then I'm gonna come to the voltage source, and I'm gonna change it to a sine wave. And I don't need any AC analysis here. And the sine wave gonna have an amplitude of 0.5, but the frequency here gonna be 100 kilohertz. So I'm using 100 kilohertz, and the output voltage, it should go all the way up to 10 volts and all the way down to negative 10 volts. But you're gonna realize that it's not gonna work as nice. The reason is we're gonna reach the slew rate. Now we're gonna define the simulation, and here at 100 kilohertz, this is gonna be 10 micro per 1 cycle. So we're gonna say that it's gonna go to 200 micro. That's basically 20 cycles, and the maximum step size is going to be 10 nano, is 1/1000. I would place it over here. Let's now run the simulation and see what we get. I'm going to plot V out. You can see V out here is not a sine wave, it's distorted. That's your Vn. Your Vn is a nice and beautiful sine wave. Remember that we're going to ignore the transient effect. We're going to look at the settling time here. You can see that ideally you should have a sine wave, and this should go all the way up to 10 volts and all the way down to negative 10 volts, but it's not doing that. It's actually going a little bit below the 8 volts here, a little bit below the 8 volts here, and it's a straight line. The reason is that the derivative dV out dt reached the maximum point, reached the slew rate, right? Because what happened is, this from this peak, from this min to this peak, that's half a period, right? It's half a period. From this min to this peak, it goes in half a period, and then in the second half period, it comes down again. So dV out dt here, the V out is max range, right? This is your, dV out, and this is your dt. So I can determine the slew rate here is basically by measuring the peak to peak, the time from this peak to that peak, over the delta t, which is something can be done easily using the cursor. So I'm going to do two cursors here. I'm going to bring the first cursor to the so I'm going to do the first cursor on the min, and the second cursor is on the max. Right? And here it tells me that what's the delta V is basically to 14.55 volts, and that was exerted in 4.762 microseconds. So you can basically determine the slew rate here by using your calculator, which is 14.55 volts divided by the delta, which is 4.7619, and this will give me 3 volts per microsecond. That's the maximum dV out dt I can get, 3 volts per microsecond. I can't get you any higher than that. So if the sine wave is changing faster than that, it's going to be a straight line, because all what the op-amp can handle is this maximum dV out dt. You end up with a straight line. It is actually distorted. I can get rid of this distortion very easily at this frequency. All what I have to do is minimize, the delta V out. So if I make delta V out very small, then I might not exceed the slew rate. And let's show you how we can do that. So I'm going to come in here, I'm going to zoom in into my voltage source, and I'm going to keep the frequency, but I will lower the amplitude of the voltage. So here I will make the voltage to be 0.5 milli. So I drop the Vn by a factor of 1,000. V out going to be changed by a factor of 1,000. So let's see now what happens when you simulate the circuit. We're going to re-simulate the circuit. That's what we end up having. You can see that the blue line is my input signal, but it reads very small. It reads basically 1 millivolt peak to peak. And this is my output voltage, right? And my output voltage is, at 100 kilohertz. It goes all the way to 10 millivolt and minus 10 millivolts, and this, a sine wave. You can see there is some form of distortion here, right, over here, because the derivative over here is maxed. That's the maximum derivative. You can see it's a straight line, right? So it's actually, there is some form of distortion. You can see it. It's over in this location here, because the derivative is maxed over here, but the derivative here is dropping. So you can see it's a form of a sine wave. I can lower the amplitude of the input signal, and it will be much better, even a sine wave at the output. This is considered distorted. So let's do it at 1 milli, and let's run the simulation. You can see it's a better response now, right? Still you have some distortion over here, but it's much better, right? You can see it's a straight line to some extent, right? So this area over here is still distorted a little bit, but not as much, right? So when you use a sine wave, it's not only the gain degrades as a function of frequency, but also the slew rate can distort the signal, right? The signal can be distorted with the slew rate, and that is also important. The reason is that the op-amp will only handle a maximum current, and there is a capacitor at the output. It's inside the op-amp, right? So there is maximum current will fill the capacitor. That maximum current that fills the capacitor will give you a maximum dV out dt, right? It's just because of the capacitance at the output and the maximum current supplied to the output. It's basically the way the op-amp works. So frequency response will affect the gain. That will affect the behavior of the circuit. And then also you're gonna watch for the slew rate, which is the maximum dV out dt. Those two important things that you need to watch when you design your op-amp as a function of frequency. Another circuit I'm interested in is the voltage follower. Let's modify the circuit to make it the voltage follower. What we're gonna do here is I'm gonna remove this resistor and that resistor to use the voltage follower. So let's remove this, and I'm gonna remove that. And the voltage follower basically is that. Sometimes we call it buffer, sometimes we call it voltage follower. Right? This is the voltage follower. Ideally, V out should be the same as Vn. V out is the same as Vn, right? Because this voltage under ideal condition is the same as this, then V out is the same as Vn. But what we're gonna realize here is that still the op-amp is a function of frequency. If the op-amp is a function of frequency, then V out is gonna be a function of frequency. So let's do the AC sweep here. So we don't need any sine wave. We're gonna apply here 1 volt. We should have a 1 volt here, right, at the output. And we're going to do AC analysis. So let's go to the simulation. We're going to say that's AC analysis. And then I will start, we'll call it a decade. We'll start from 1 hertz. And that will go all the way to 10 meg. Oops. Those are the number of points. It's going to be 1,000. And then this is going to start from 1 hertz to 10 meg. We'll put this over here. And let's run the AC sweep and see what we have. So because the input is 1, the output is the gain, right? Because, you know, output over 1 is the gain. If the input is 1 volt, the output is the gain. This is our gain. Now, a couple of things are interesting here is that the gain going to be 0 dB. It's a unity gain, right? It's a unity gain at low frequencies. You can see that. But then you have the speaking effect. The speaking effect is a second order system. It's underdamped system, right? It's basically called peaking effect, right? So the peaking effect here happens because the op-amp itself is a function of frequency, but also we use a feedback. So it becomes a second order system. It's very interesting to see that, which means that if you apply a step response, you're going to have underdamped response, right? So you're going to have some form of oscillation. So the cutoff frequency is around the peak here. So this is the cutoff frequency of your system. The peaking is not bad. It only went 2 dB above the ideal case, which is the 0 dB. But let's do the cursor and see at what frequency that peaking happened. So this peaking happens roughly around the 3 megahertz, more or less. Around 3 megahertz, we have the peaking has occurred, which basically shows us that there is it's an underdamped system. So now we're going to investigate the underdamped system, and let's see if we can show you that it's going to be on an underdamped system. So what I'm going to do here is I'm going to apply a rectangular pulse, and that will do transient analysis. That will show you that it's going to be on an underdamped system. Again, this frequency response makes sense because the op-amp going to degrade as a function of frequency. The gain is 0 dB, and then it's going to follow the op-amp, and the op-amp going to degrade as a function of frequency. So let's show you how we're going to do that. Basically, I'm going to remove the AC sweep command, and then I'm gonna make this a pulse. So the pulse will go from let's say that initial will be 0, will go to 1 volt, and then the time delay we're gonna make it 0, time rise 1 nano, time fall 1 nano. I'm gonna make the T on to be 10 micro. I already did the simulation before with the OP27. The 10 micro is good number for the pulse width. Usually you do that through trial and error to decide. So what you want to do is you want to zoom in and tune it. So that's what I'm doing here. I already know that 10 micro is going to be a good value. And then I'm going to make the pulse width going to be 20 micro. I don't need the AC component here. This is basically the value of the voltage. I'm going to move it a little bit closer to the voltage source. And then here I'm going to add the simulation. So I'm going to basically say edit simulate command. It's going to be transient. I'm going to make it go for 2 clock cycles. So this is going to be 40 micro, 2 clock cycles. And then the maximum time step, the maximum step size, I will make it 1 nano. It will be a little bit slow, but it's not too slow. The higher the resolution, the slower the simulation gonna be. 1 nano here gonna be a good number. So I'm gonna place the simulation command over here. Let's run the simulation. Now I'm gonna plot V out. You can see that a couple of things happened here. The first one is this here is the slew rate. So this here is the slew rate, and then that is the simulation that we are expecting. So to get around the slew rate, what I will do is I will lower the input voltage. So let's go back here, and I will make this to go like 10 milli, for example. Let's delete that. So you can see that you still see the slew rate, but it's not as dramatic. And now you can see that here is the sine wave as it goes up and down, right? So you know, it's a second order system for sure, and it does have that step response, right, that we have. That's what was expected, because we have peaking in the frequency response. We end up having overshoot. This is called overshoot. It's not bad. 20% overshoot is not a bad metric. If it goes too high, it might have stability issues. So with that, I would like to conclude the first lecture. This is a very good lecture to have. Good luck to you.